Hi there. My name is Denny Lee, and I'm your host today for this awesome tutorial session on how Delta Lake supercharges data lakes with Louis Frolio. We're going to start in about 2 minutes. So note that we will start very shortly. We will be answering your questions via the Q&A. So on the bottom of your Zoom, if you're using Zoom, click on the Q&A and ask your questions there. Or if you're on YouTube Live, no problem at all. There's a live chat. So we will be also on that to answer some of your questions there. Zoom will be a little bit more straightforward, to be honest. But if you're on YouTube Live, don't worry. We're going to be there to answer your questions as well. So as we're waiting for people to dial in for the next minute or so, if you want to chime in on the chat and tell us where you're from, what city you're located. My name is Denny Lee. I'm your host today. I'm based out of Seattle, Washington. So in this case, sunny Seattle, which I know many of you don't believe, but that's where I'm from. Louis, where are you from out of curiosity?
Hey, Denny, I'm just outside of Boston, Massachusetts.
Perfect.
And it's not sunny here either.
It's not sunny? Oh, okay, sorry to hear that. Okay, we got somebody from New York City, originally from Paris. I wonder if that's the same person that I was talking to from 2 days ago. If it is, that's awesome. Bonjour, ça va? Hope things are going well. Yes, you are the same person. That's awesome. Perfect. France, Montpellier. Sunny as usual. From Montpellier. That is awesome. Well, bienvenue. Welcome aboard. Glad to have you here. Oh, cool. We've got somebody from YouTube Live. They're saying they are from New York. Awesome. That's a good thing. Oh, and we have Manish from Seattle. Hey, Manish, how's it going? Cool. I'm going to, instead of actually going through the chat right now, it is 2 past the hour. So Louis, why don't you take it away and start the show? As noted for everybody, if you have your questions, please prop them in the Q&A, not the chat for Zoom or YouTube Live. We're going to, myself will most likely answer your questions while Louis is going to go ahead and run this tutorial. All right, Louis, take it away.
Thank you, Denny. So welcome, everyone. A bit about me. My name is Louis Frolio. I am a senior technical instructor here at Databricks. Been with the company about 8 months now. Best job ever. Prior to Databricks, I came from IBM, where I was a technical evangelist. Prior to that, I worked for EMC Corporation as part of their big data solutions team, where I helped with technical enablement. And prior to that, many roles throughout my career as a data architect. I'm a data guy. I live in the data space. And so very comfortable here at Databricks now. Personal interest, I was a chef at one time. Nice fact about me. I still cook today. I like to travel as well, although I'm not doing that. I probably won't for another year. And then I'm a big fan of teaching and mentoring. Currently, I mentor with a company called American Corporate Partners, ACP. And what they do is help active duty military people who are, long-term, had careers looking to transition into the private sector. So I help out with that. So every year I take on a new person and I help, get them out and into a job, usually, analytics related type jobs. So I enjoy that very much. And then here, LinkedIn, please feel free to connect with me. I'm always happy to expand my network. All right, let's get going here. All right, so how Delta Lake supercharges data lakes, right? So here, Delta Lake's transaction log, it brings high reliability and performance and ACID compliant transactions to data lakes. And so how does it do this, right? That's the goal of today's tutorial, right? I want to walk you through a close look at the transaction log mechanisms within Delta Lake and how it accomplishes all the great things that Delta Lake does, and which I will go through in a moment, right? So we're using for this tutorial, it's going to be the open source Delta Lake. And in fact, this entire environment I am in is open source. All right, I'm running on CentOS 7.8, Spark 3.0, Delta Lake 0.7.0, Scala 2.12, and then Jupyter Lab 2.15, right? Installing Delta Lake is trivial, right? You simply need to have an environment with Spark 3.0 running if you want to run 0.7.0 of Delta Lake. And you just have to, go to the Maven repository and download the jar file, put it into Spark Home jars. And then there are multiple ways to configure Delta Lake to run in the Spark session. I'm going to show you one particular way, the way the most convenient way for me to do this tutorial, that is. Source data for this notebook comes from the UCI Machine Learning Repository. It is UK online retailer sales data. If you want to learn more, I put a link here too. So when you go to the GitHub repository for all these lessons, this notebook will be there and you'll be able to do that. Just so a bit about Delta Lake, right? So Delta Lake is this open source storage format, right, that brings ACID transactions to Apache Spark and big data workloads on top of data lakes, right? So data lakes being, it could be HDFS, it could be cloud storage, AWS 3 or blob storage, Azure, right? It's a layer that sits on top of that. And what Delta brings to the table is it's an open format, right? We use parquet file format under the hood. We don't make any changes to it, right? So there's no lock in there when you use Delta format. Delta provides ACID compliant transactions, right? Just like you would see in a relational database. It has schema enforcement and schema evolution. So unlike traditional data lakes that are schema on read, Delta Lake is schema on write. So it helps ensure your data is consistent and doesn't become corrupt. Delta Lake provides a complete audit history of what's happening on a particular table or a set of tables, right? You can track through time the provenance from creation to the current state of that table. Delta Lake provides the ability to do time travel queries, so you can go back and query the table as it were at an instance in time, either by timestamp or by table versioning. Delta Lake supports deletes and upserts on tables, right? It has scalable metadata management, right? So you're going to see that as we go through Delta Lake and I show you all the cool features, you're going to see these transaction logs being created. And depending on, how you set it up and how you use it in your organization, you can end up having quite a bit of metadata there, right? But there's no worry because, it's running on Spark and Spark is designed to accommodate big data. So no worries with that. And then finally, Delta Lake supports unified batch and streaming on source and sync. So here's a nice image demonstrating, Delta Lake here. It's built on top of Parquet, and it's these transaction logs, what I call the secret sauce behind Delta Lake, right? That provides all of these cool features that we just went through. Within Delta Lake, right, if you have a Delta table, it supports batch loads, it supports streaming loads, and then supports updates and deletes. With Delta tables, you can do batch loading and stream loading at the same time while someone else is reading the table. So it's very powerful, right? Through all of this, right, Delta provides that high quality and reliable data. All right, so let's dive in here. So the way this is going to work, right, I have this Jupyter Lab notebook here. I'm going to talk you through just some quick setup and helpers and configuration, how I standardize on data file pathing. We're going to download some data. We're going to define schema. We're going to do just some quick, clean and exploration of that data, right? I'll walk you through, how our Hive Metastore is going to be set up. And then I'll go through a few cells of working with Parquet files just to remind everybody, how Parquet works and what it looks like. And then we'll dive right into Delta Lake with all the cool features and looking closely at that transaction log, right? That's the purpose of this tutorial, is to really look closely at that transaction log and what happens. And then I'll talk through some administrative features, file compaction. We'll have a look at time travel, and then we'll talk about vacuuming and data retention. All right, so setup here, right? So we start off just, loading up our required classes. Here, I'm going to create the Spark session that will be used in this notebook, right? So a couple things, the Delta, that jar file, what we installed, right? Here's how we reference it, right? And this is just one way of instantiating and connecting with Delta Lake, right? I'm going to do it right here in the session. It makes it easy. Another configuration here is the Delta Spark session extension. And that just enables, Delta Lake specific SQL support with Apache Spark. And then down here, the catalog, Delta catalog, it's going to enable integration with the catalog APIs so that we can use the Hive metastore and all that good stuff. Right. And then here I'm setting up my shuffle partitions and default parallelism. Generally, you want these to align to the cores, right? The number of cores in your cluster. I have a VM running here and it has 4 cores, so I'm going to set that to 4. And then finally, I have another notebook. And by the way, this notebook will be part of what Denny puts up in GitHub in a helper function. And it's a helper function I need to look at the files on disk, just to make it easy from within the notebook to be able to reach out to the file system and have a look at the data that's there. A general best practice, something I like to do, and it's something that certainly we recommend at Databricks, is to standardize on your pathing. It makes your code much more readable, and it'll save you on typing down the line. Right down here, I'm just resetting everything, so I'm able to rerun this notebook over and over without any issues. Next up is the code to download that data. Right, the data, the reference is to the UC Irvine machine learning repository, but I'm actually pulling down the data from GitHub, Databricks, GitHub, and it relates to the Spark, the definitive guide book. The data is nice and formatted there, so we do that, right? And all right, and so I went and I looked at the schema of this data, right? And so I do want to define a schema when I work with this data in these data frames. It's Spark requires data frames, require schemas. And as most of you probably know, you can do infer a schema where Spark will figure it out. We don't recommend that. That's not a best practice. You should always define your schema, right? So, let's have just a quick peek at that data that was downloaded, right, in text format here. Right, we can see we have the first row is just the column headings and then just a bunch of tuples of data, right? This is the schema that corresponds to that, right? And this here, I'm using the SQL DDL method, right? There are other ways you can do the struct type. I put the code in here if you're curious how to create a schema with the struct type. For a simple flat schema like this SQL DDL method works fine. If you have schemas that have nested attributes or nestings within nestings, you're probably going to want to use this struct type method. That gives you more control. All right, so moving on to our data here, right? So I'm defining a data frame here to read in that source data. I'm providing the schema, and I'm going to do some simple metrics on it just to see what we got. All right, so we have 541,909 records, and it came in with four partitions, right? So because I have the 4 cores, I set the default parallelism, and so we see there were 4 partitions. This data, some of the queries we're going to be doing, right? We have to ensure that some of the data does not have any nulls in it, right? And so looking at all of the columns, looping through the columns and looking for null count, I can see that there are invoice records that have invoice numbers that are null and records that have customer IDs that are null. Same with description. I don't care so much about description, but the invoice in the country customer ID is important. All right, so I just want to clean that up, and that's what this code is going to do right here for us. It's going to remove those records, all right? And now I see that there are no more nulls. However, I did lose 143,985 records, but that still leaves us with this, 397,924, right? So what I'm going to do now is create a new data frame based on our clean data, right? And I don't need all of this data for this demo. I don't need all 397,000 rows. So I'm just going to take a fraction, 25% of it. And I am going to set a seed so that this is reproducible. Every time I run this, I'll get the same results, and that's what the seed is going to do for us. And just having a quick peek at our data, right? It's not nothing surprising here, right? Okay, so now we have our data frame. We worked with the data frame API to manipulate this data and do some minor cleanup on it. Moving forward, we're going to want to work with SQL, right? So Delta Lake was designed to accommodate OLAP type use cases, right? And so generally in those use cases, you're going to have folks that are, many more folks that are comfortable with SQL compared to, say, PySpark or working with the data frame API here, right? So we want to set up our Hive metastore so that we can create tables, SQL tables to work with. Right, and so this code here is just going to go ahead and ensure that I have a database called Delta Demo right here, and that it's empty. Right, so if I run this through this entire script, I'm going to end up with some tables. This is just going to clean them up. So we can see here that I do have a database called Delta Demo, and my current database is set to that database, Delta Demo. And here's some information metadata about it itself. It lives down this path on my local file system, and there are no tables in it at all. It's empty. So let's move on and look at Parquet, the Parquet file format briefly before diving into Delta. All right, so Parquet is the default file format for Spark. Parquet is very efficient. It's quick, it's fast, it's compressed. And so it is the default file format for Spark itself. And I'm just going to start off by creating a table, right? So that data frame I created a few cells back, retail sales data 1. I'm going to create from that a table called sales Parquet format, right? And I'm going to save it in this path. So when I run this command, a couple things. One, that Hive metastore, right? That database that I created will have the metadata for this table, all the information, right? And so, what metadata you ask? Well, it's the metadata that it got from the data frame, right? So the column names, column types, right? And the table name itself that I gave it, that's persisted in the Hive metastore. The second thing it's going to do is actually write this data out to the file system. So when Spark writes data to the file system, it creates a directory, and within that directory, it will place the files. In this case, it's going to place Parquet files, right? And so right now, I've run this. This table has been created, so it's in the Hive metastore, and that data is out on disk, right? I can look through the command spark.catalog.list_tables. It will query the Hive metastore, and I can see that my table is in fact there, right? It's in the database I wanted it to be in, and it's in a table type as external as well. That just means that I'm managing the data for this, the pathing and the cleanup of that data, right? And so when it writes, I mentioned that it creates that directory of files. Let's have a peek in there and see what we got. Right. So in this case, that table I just created, it created 4 Parquet files here. Right. Not a big deal. It's just, again, that the 4 is tied to the parallelism defined within my environment and associated to the cores I have. I can do a describe extended on that table as well. Right? I can see my schema, the database it's in, the table, the provider, right? Statistics, location, etc. Right? Just like you would do in SQL itself, right? You're able to do that here within Spark. And then finally, I can go ahead and I can select from that table, right, using Spark SQL right here, right? So spark.sql, and then putting my SQL within those those quotes, I'm able to go ahead and see that data, right? And it's what I'm expecting. So with Parquet, we're able to, insert into, right? Actually, it's more, think of it more as of an append, right? So Parquet files are immutable. When we go to insert data into that table here, those 4 original files will not change, right? What we're going to see is that a new file gets created, right? So I'm just going to add 1 record here. And what's going to happen is we'll see that we have that 1 file right here, right? And if I were to put the path in there, I'd be able to see the record I just created, right? So, you know, above we just saw how to create table structures using Parquet and using the Hive metastore, right, to store that table metadata, right? We use SQL to query and insert data into that table. However, there's no history, there's no detailed history of these events that took place, right? I just know the current state that I'm in right now. But I can't go and look and say, you know, what happened along this timeline and what are the details of what happened along that timeline, right? The best I can do is look at the creation times of these files and sort of guess, you know, when they were created, right? So Delta Lake, right? Delta Lake, as I mentioned, is that it's an open storage format, sits on top of data lakes, and it provides all of the features that we mentioned. Working with Delta Lake is easy. Instead of specifying the format as Parquet, we just need to specify it as Delta. Pretty straightforward, right? And so here, I'm going to take that data frame that we created earlier, right? And I'm going to go ahead and write it in Delta format to a new path that I call Delta path here, right? And then we're going to go ahead and select from it. Now, it should look no different than when we did this with the Parquet, because under the hood, right, the storage is our Parquet files, right? So it looks the same. And so here we're doing a query on it, right? And what's neat here is that I can actually run SQL against a directory, right? So here's my Delta path. I just need to preface it with Delta dot, and I'm able to query that directory just like I would if it were a table, right? We're going to create a table in a minute, but here I just wanted to show you. And this works for Parquet as well. This isn't exclusive to Delta, right? Okay, so for that particular path, I want to create a path-based Delta table, right? And I'm going to put it into a variable. And once I do that, right, with Delta, I can look at that history. One of the closing statement I made about Parquet was I don't know the history. I don't know, the provenance of that table from creation to current state. Delta Lake does all that for us, right? And it's these transaction logs that we're going to look at in a minute that enable that to happen. So here, right, I have this path-based table definition, and I'm going to say, give me the history of it. And then there are many more attributes that you can look at. I'm just taking a select few here, right? And we can see that currently the Delta table, we're at version 0, right? The initial creation of it. And then we have this metadata about what happened to this table at that point in time, right? So at this timestamp, there was a write operation that occurred. All right, the mode was overwrite. That tells me this table was created at this point in time. And then we have these operation metrics, right? We saw that 4 data files were created. We see the total size of it, and then the number of rows that were written, right? So I showed you when we wrote that Parquet file, it created 4 Parquet files. Delta uses Parquet, right? And so we wrote the same data frame out to a Delta format, and it created 4 files, right? And so here is the directory of data that was created when I wrote this Delta data out. Notice here are my 4 Parquet files, nothing special, standard Parquet files. However, we do have a directory, right? We have a subdirectory. And it's always called _delta_log. So when Delta writes data you create a table or write data out to the file system. Within that directory of data, Delta is going to create a subdirectory. And within that subdirectory, it's going to keep its transaction logs, right? So if we look in that directory, this command here just looked inside there. I can see there's one file, right? It starts with 0 and it's a .json. Let's have a look inside that JSON file, right? So there's a lot in here, right? But notice, right, just at the top here, right, we saw that there was an operation of write, 4 files were created, output bytes, right, a bunch of stuff. This looks, similar to this, right? So when you run this history command, right, Delta is going to actually go through the relevant transaction logs and put it in a much prettier format for you. That's what it's doing for us. This is the raw transaction log file itself. We can see right here all the files, parquet files that were created. You can see in here the schema, right? When it creates the table, it's going to actually, within the transaction log, write out the whole schema for you. And then it's going to have other information about the protocol, right? This relates to the versioning of Delta Lake to be able to read and write, et cetera, and the creation time as well, right? So quite a bit of relevant information in this transaction log. So at this state in time, Delta Lake is fully aware of the state of that table based on this transaction log. Right, so let's go ahead and add some more data and see what happens, right? So I'm gonna create another data frame off that clean sales data frame that we created at the top. I'm only gonna take a fraction of it again, and I'm gonna change the seed with the hope that most of the records are, to get a different set of random records, right? So let me just go ahead and run that. All right, so this came back with 99,149 records. And here I'm going to go ahead and append that, right? I'm going to take that data frame, I'm going to append it to my Delta table out on disk. And then we'll take a look at the history here. I'm expecting, well, let's see what it says. All right, so here's the history, right? So we can see the table is now at version 1, right? The last thing I did was a write operation. The mode was append, right? I added 4 files. So I have a total of 8 files out on the file system right now. And then just, the size and the number of rows. Right, and so here are those files. Here are the 8. Here are the original 4 when I initially created it. So this is ordered by time. And here are the new 4, right? So these 8 files now make up the data of for the current state of that table. All right, let's go look at the transaction log, right? So whenever we have a DML operation, right, we have data we're adding, deleting, or updating on a Delta table. Those are all transactions. A transaction log is always created, right? So so I'm sorry, my Slack just interrupted me. 0 was the original one, and now we have a new one, right? So let's have a look in there and see what we can see, right? It's much smaller, right? Because we don't need to rewrite the schema. The schema was already addressed in the first transaction log, right? So Delta is fully aware of the schema, right? Because it would just need to read this transaction log here. And so this one, it's just the new files that we added, right? And then we can see, the write, it was an append. And this read version, right? It's wrapping right here. It starts right here, right? That's saying that this transaction, Delta read from version 0 of the table to get the information to be able to write out, the data, right, which becomes version 1 of the table, right? So it tells you what it read from. And so you can see sort of the pattern of what's happening here as these transactions go through. The transaction log is going to capture that information, and Delta is going to use that, right? So that when it needs to, reconstruct the current state of the table for queries, it's able to do that easy enough. And you'll see soon enough that also, these transaction logs are going to be used to help with time travel queries. All right, so let's move away from our path-based table and just go to a straight SQL table now. All right, so I created this. It's called cells delta format. If I do the catalog, query the catalog again and list the tables, I can see that my table is created right here. Right, so I have the original parquet table and I have this delta table. Right, and what I want to do now is to step through some DML operations. We worked with inserts so far, adding data. Let's look at what happens when we do updates and deletes. Right, so the first thing I want to do is just generate a random invoice. Right, I'm going to go out and query my data and randomly pick an invoice so that I can pick on that invoice throughout the rest of these DML operations, right? So if we have a peek at it, right, we can see this is what the record looks like. Now I added this virtual column. It's called the input file name. And what it's going to do, what it does is it shows you the actual file, the parquet file that this record lives in, right? And this is going to be useful for us. We're going to see, it's going to be useful in a few minutes here. All right. All right. So I have this invoice number here, right? And I want to actually add another line item to that invoice. And that's what I'm going to do here. Right. I'm going to add a record, the world's best jam making set. All right. So let's add that. Right. So this is the insert similar to what we did before. So I expect, we before this operation here, I had those 8 parquet files. I just added another parquet file. Right. Right. So let's look at the JSON for that. This is the transaction for that insert I just did. Right. Let's have a peek inside of it. And we can see here that, in fact, we did add another parquet file. And then the operation was a write and an append. And you can see that read version incremented, right? It had to read version 1 of the table to get the information needed to be able to do the write, right? Pretty straightforward. Number of output rows 1, because I only inserted 1 row. Right, so now we can see there are 2 records, right? And each of them, the original is right here, this guy. And then here's the one I just added. So these 2 records live in 2 different parquet files, different files altogether. Right. So now let's see what happens when I make a change to this invoice. So what I'm going to do in the next step is just add 1,000 to the quantity of each of these. Right. So after it's run, I should see 1,006 and then 1,005 here. All right. So I'm using SQL for that. You'll see throughout this, this is a side note. I put in the data frame API syntax if you're more comfortable using that over SQL. Right. All right. So I just updated these 2 records. Right. Let's go ahead and run that select again. Right. And we can see that, in fact, the quantity is now 1,006 and here it's 1,005. I want you to notice, though, the file name. Right. The file names have changed. Right. It's changed because, again, those parquet files are immutable. If we make a change to data that's in a parquet file, what's going to happen, Delta is going to grab all that data. It's going to read it. It's going to apply the changes, and it's going to write a new parquet file, right? So that original one here, right, it had to rewrite that one. And then the one here, right, it had to rewrite that as well. So it just added 2 more parquet files to our directory of data. Right, and so let's look at the history here. We're currently at version 3 of the table. The operation was an update. And look here, whenever you do an update or a delete or a merge, Delta is going to capture the predicate. Right. And so here it was an update where invoice equaled this. Right. So that's pretty cool. It's going to capture, all of the operational metrics. as well as, for DMLs, it's going to capture the predicates. So again, you want to be able to see that table's journey from creation until current state. And so 2 files were removed for that operation, and 2 were added, and 2 rows were updated. Here, when it says files removed, they're not physically removed, right? Delta, by going through these DML operations, is not going to physically delete our records. When it says remove files, actually what it's doing, it's putting a tombstone marker on that file, right? And that indicates that that particular file is not needed to be able to query the data in the most recent version of that table, right? It's not needed for that. However, it might be needed for time travel queries, right? So that's why Delta is not going to delete these when these DML operations happen. All right, so if we look in our folder of data files, right, we can see it's growing, right? And this here was the last operation. That's the update I did, right? It pretty much had to rewrite all of that data, right? And so it created this big old file right here. And so as we go through these DML operations, the list of files is going to keep growing and growing, and the list of the number of transaction logs is going to keep growing and growing, right? So we're up to this is the 4th transaction, but it's 0 based, so it's 3.json, right? We can see here that we had 2 files that were removed, right? And it's going to tell us what files are removed, and 2 new files replaced it, right? So these transactions, right? They are keeping an accounting of all of these files that are being added and deleted as particular operations happen, right? So I said when I did that update, those files were deleted. They weren't deleted. They had a tombstone marker put on them. Essentially, this here is, the way that Delta knows that this file is not needed to be able to return a query based on the current state of that table. Right. And so here, right. So here's just looking at that table data again, right? To remind us what it is, because I'm going to go and do a delete now, right? So those records are there. I want to actually do a delete. So I want to delete them. I want to remove them from the data set. All right. And so again, just using SQL, I can go ahead and do that. And just like before, I put in the, here's the syntax, the data frame API syntax to be able to do the same. Right. So now those records were deleted. They're not there. Right. When I ran this query, Delta, because I didn't specify a version or any time travel, Delta is going to look at the most current version of that table. The most current version of that table does not include those records anymore because I deleted them. Right. And looking at the history again, all right, version 4, it was a delete operation. And again, here's that predicate. So we know what happened, that this was what the delete was based on. There were 2 more data files removed. 2 new ones were added. 2 rows were deleted and 1 file was added, right? So this time it only added 1 file, and it only added 1 file because the invoice I just deleted, right? There were 2 rows. 1 row lived in the original parquet file with all the other records. And then that second row that I added, it was the only record in the parquet file, right? So if I delete it, there's nothing for Delta to recreate, right? So it only had to take that first parquet file with the record that I was deleting, along with all the other records. It just had to recreate that minus the record I was deleting. Right. So we got all these deletes going on, and we can see that, our parquet files are growing. We're getting more and more parquet files, right? If we look at the transaction logs, right, this is transaction 4. Right, we have a peek in there. Right, again, it's showing us what was removed, what was added. Let's see, Spark catalog, yeah, the table that was impacted, right? Let's now have a look at um, how these transaction logs are managed, right? We know what goes in them. We know that Delta is reading them to understand the history of the table. But these things keep growing and growing and growing, right? If you count, there are 20 zeros in front of the period here, right? So the intention is that you're going to potentially have a lot of these, right? And so Delta, right? Every 10 transactions, it creates what's called a checkpoint, right? So a checkpoint means it's going to look at the prior 10 transactions and roll up that information into that parquet file, right? So that's what I'm going to do right here. I'm going to force a checkpoint, right? I'm going to have 5 transactions happen, and it's going to force a checkpoint. All right, so let's let that go. And so what I expect to see when this finishes is, it'll stop with 10.json, and then those are the 10 transactions, and then Delta creates a parquet file with all of the transactional information that led up to it, right? Right. So here we go. Within this checkpoint file, right, is all the information needed by Delta to be able to reconstruct the current snapshot of the table, right? It's not going to help. It doesn't necessarily help with the time travel queries, right? Delta is going to need all of these past transaction logs for time travel. But this here is a roll up of all of the parquet files, right, that are needed to be able to construct that current image of the table, right? So let's just have a peek in here and have a look, see what that looks like. Right. So admittedly, this isn't nice to look at, right? But we can see there's a column add and column remove, and there's a bunch of files in there. What I want to do is just clean that up a bit. Right. So what I'm going to do is create a view and reorganize that data. All right. So it's a little better, but I really want to see it all in one table with it sorted by the date. Right. So that's what we're going to do here. And then let's do a select. Right. And so here we are. Right. If you follow these records from the start till the end, right, you're going to find that it doesn't start with the initial, well, it may, but it doesn't necessarily have to start with the initial parquet files that were created, right? Because Delta doesn't necessarily care if a particular file was deleted and replaced. What it cares about is right now, is it able to reconstruct a current snapshot of that table, right? And that's what it's able to do here. So if Delta were to read this to do a query on the table in its most recent version, right, it's going to look at all these that have the adds, right, because the deletes don't apply, right, so much. And so this is important, right, because Delta doesn't need to be able to keep all those transaction logs or have to open all those transaction logs. In fact, Delta caches these into memory, right? So it has fast access to, the transaction logs, the current state of the table itself, right? And here, let's go back here for a second, right? So what's going to happen is when another transaction, 10 transactions occur, Delta is going to create another checkpoint. And within that checkpoint, it'll have all the files it needs to be able to, answer questions on the current version of that table, the most recent version of that table. All right. So another nice cool feature about Delta is this merge capability, right? The upsert. It plays well into, change data capture type use cases, data warehousing, updating dimension fact tables, right, of the sort. Delta, it's pretty straightforward, right? Here's what it looks like in SQL. Right, you can do this with the data frame API syntax as well, but it's not nice to look at. It's harder. Here, it's just straight SQL. And so the way you do it is, right, you start with the table, you merge into the table that you want to update, and then you have to specify the table or the view you want to use, right? It has to be a view or table because we're doing a SQL join. And that view right here is created. I create it right here. I just take a tiny fraction of the data. It's like 4 or 5 records. And then I create a data frame of that. And then that data frame, I go ahead and do a create or replace temporary view. And I call the view this right here. Right. And so here I'm joining the table in that view on these 2 keys. And what I'm saying here is when you find a match, just update all the rows on the target, right? Take the entire row and update the target, right? There's a lot of flexibility here though with this update. You just don't, you don't have to specify replace the whole row. You can specify individual rows. You can do calculations to update the target row based on the data coming in. You can even set it up to do deletes, right? But here for simplicity, I'm just specifying I want the whole row replaced. And when it's not matched, meaning the data is not present, just go ahead and insert it, right? And what's neat here is that this whole merge, along with all the other DML operations that we've done, the deletes and the updates and the inserts, right? They conform to ACID compliant transactions. So if this is a big update here, so you got a lot of data that you're merging in, because it's ACID, either the entire thing is going to succeed or fail. It won't ever leave your table in a partial state. And that's the same as well for the other DML operations. If you have someone writing to a table and someone's reading it, right, they won't, because it's ACID compliant, they're not going to collide with each other, right? The reader is going to have a consistent snapshot of the data that they're looking at. And the writer is going to be able to write or make updates, and not be impacted by the reader, right? So all of these are ACID compliant, and which is pretty cool, right? All right, so let's look at the history again here. Here's the merge statement. It sort of blows everything out of proportion here, but again, the entire predicate for that merge is part of the transaction, right? So again, you're able to see what happened to that table through time. Right, and then, I just wanted to show you this here, right? So this transaction was from the merge I just did, right? We can see that for that merge, we had to remove, I think it's eight files, and we added 4. If I go and look at the files that were written to disk, right? These are the actual count of files out on the file system. 28. There are 28 parquet files. However, if I look at that table, that checkpoint file table I created, this thing right here, I only see 24 files. And that's because the checkpoint table I created only has information up to here, right? And up till this point, at this point in time, there are only 24 parquet files out in the file system. But I just ran the merge, right? And it created 4 more, right? And so what Delta is going to do, right, when we do when it goes and does the history or looking at sort of how that table is progressing through time, it's going to start with the checkpoint, and then it's going to look at this file here to get the other piece, right? And so that's why we see only 24 when we look at the checkpoint table, right? That only goes up to this point right here. But if we look at the physical files on the file system, there are 4 more, and that's because of the 4 that were created here in that 11th transaction. All right, so it should be clear that as these transactions happen over time, files are going to be added, and depending on the use case, right, how you use Delta, say you have structured streaming jobs that have triggering events every minute or so, right? you're going to end up with a lot of parquet files. You're certainly going to end up with a lot of transaction log files, but the parquet files are, that can end up being a problem, right? So if you find yourself with, 15, 20, 50,000 parquet files, right? Spark has to be able, to be able to read that data. It's going to have to open all of those files, right? And that can be time consuming. So you want to do file compaction, right? And that's just reducing the size of the number of the files that you have. So, and this corresponds to what we call the small file problem. If you have many small files, it's going to be, you're going to have a performance hit on queries, right? And so here I want to actually create an artificial small file problem. I'm going to take my data, which is 28 files. I'm going to turn it into 1,000 files, right? 1,000 smaller files, right? And so when I go to query this, Spark's going to have to open up all of those files to get, all of the relevant files to get the information that it needs, right? So if I go out, I can see now that I have 1,028 files out on the file system. And I'm going to go ahead and run this query, which is doing a group by an account. And I'm going to time it and see how long it takes. All right, so the wall time is what we care about here. It took 1.2 seconds to run this query, with Spark having to open, the 1,000 some odd files that it needed to open. So now I'm going to compact those 1,000 files back down to 4 again, right? And we're going to run the same query. Right, we can see that we now have 1,032 files because, again, these operations aren't deleting files, physically deleting the files. So we had 1,028. I compacted it down to 4. And so now we have 1,032. But of the 1,032, only 4 are needed to run a query against the current state of the data. So here's the same query that I ran above that took 1.2 seconds. Now it's compacted, less files need to be opened. I expect to see a performance gain. And I do. It's now it took 329 milliseconds, right? So that's significant. That's a significant speed up. And you can imagine as the data gets really big, this isn't big data. As the data gets much larger, you'll see bigger improvements on that time. I want to talk briefly here about time travel queries, right? With time travel, you're able to go back and look at a table as of a particular version. So let me scroll back up here. So right here, we can see these versions, 11, 10, 9, 8, 7, 6, right? You can write a query to query up against that particular version of the table based on the version, or you can do it by timestamp as well. All right, version just makes it easier, in my opinion, than trying to format that time and figure out the time. Right, so we can see here that we are currently at version 13 of the table, and it has 198,400 rows of data. Right. Right, and so here we can see from the history, right, that we had 4 files were added, right, to the system. So this is right. This is version 13. There are only 4 parquet files, and that represents the whole of the current version of that table. I'll compare it to the original, right? So here we see there are 99,174 more rows in version 13 than version 0 of the table. So a lot happened from version 0 to the current version, right? And so you're able to, do these queries with this time travel mechanism, and it's because of these transaction logs and the versioning that Delta imposes on these tables every time a transaction occurs. Because of that, you can do rollbacks, right? So say you accidentally delete some records in a Delta table, you just need to roll back to the prior version. And what I'm going to do here is I'm going to roll back to version 0 of the table. I'm going to take it back to its original state. So our current version is 13. The data looks a certain way. I'm going to roll it back to what it looked like at version 0. right? And so here, I want to test that that actually happened. I want to compare the record count of the current state of the table to the record count of version 0 of the table. And so that's what I'm doing right here. I'm looking for equivalency between the current version and version 0. And it should come back true, right? So I successfully rolled back that table, right? And that last transaction was transaction 14, right? And you could see the mode was an overwrite. Right? It was a write with the mode was with an overwrite telling me that I recreated that table and 4 files were created. All right, so that's pretty cool that you can go back to prior versions, roll back, or you can query as of prior versions. All right, the last topic here is about data retention and vacuuming. Right, so with Delta Lake, as you saw, as we move through time and we're adding records, modifying records, files are being created. Some are marked with a tombstone marker, meaning they're not needed for the current state. You may not want to keep a history of data around. You may not be able to, right? So say, think of a GDPR use case. I call and I say, please delete my data, right? And then the tech goes in from their Delta table and they delete Lou Frolio from it. We know that at that point in time, they're not GDPR compliant because the only thing we did was create a new version of the table without my information. However, those older parquet files are still there with my information, right? And so that's a use case where you may not want to keep data around, right? And so we have a mechanism called vacuuming that'll go and clean up, right? So look, here we have 1,036 files in that directory. And vacuuming is pretty easy, right? You just say vacuum. This is using SQL. The table name, and then you have to specify the number of hours you want to retain, right? And then this dry run here it's just a dry run. It's not going to actually delete it, right? But here I'm saying 0 hours. I want no history. When you're done with this vacuum, I only want those 4 files. And so, oops, when I run this, all right, we get this error message. It's saying, are you sure you would like to vacuum all the files with such a low retention period? If you have writers that are currently writing to this table, there's a risk that you may corrupt the state of your Delta table. You could also, if someone's doing a time travel query and you run a vacuum and you remove all the data, their query will fail, right? So Delta puts in these guardrails to keep this from happening, right? Because it's recommended to keep 7 days or 168 hours around. Right, so to override that, we have to set this retention duration check dot enabled to false, and those guardrails are gone. And then I can go ahead and run this vacuum, right? And so this is going to take a couple seconds, but what's going to happen is Delta is going to go through the transaction logs, right? And it's going to say, what files what files are not needed anymore for the current snapshot of the data. Right, we saw here that there were 1,036 files out in that directory, right? Only 4 of them are needed right now, right? Because we rolled back to version 0 and there's only 4 files for that. So it's going to remove 1,032 files for us, right? And so this should finish up in a moment here. There it goes. All right. So now it took 36 seconds, right? So if we go and look in that directory, we only see the 4 files that are needed, right, as well. And so, yeah, there we go. All right. All right, just doing a record count. So by default, Delta has a 30-day, it sets a 30-day window of deleted files that'll keep around and 30 days for transaction logs. So after 30 days, being 30 days old, Delta is going to start cleaning up the transaction logs and those deleted files. You can override that, right, by just doing at the table level, right? You have to issue an alter table statement against the table, and you set these table properties. So here I'm going to set log retention duration to 7 days. In other words, I only want to keep 7 days of log files around, and same with the deleted files. Yep. Denny, I'm finishing up right now in this last statement here. I just want to show everyone that within the describe extended, I can now see those table properties exist for them. So with that, I'm sorry I went right up to the time. Denny, go ahead and take it.
Thank you very much. Louis, I really appreciate you taking the time to prop this tutorial. That was awesome. I did also want to call out that this video is on YouTube Live and the notebooks are there as well. I'm going to go ahead and share my screen just for a second, just because I wanted to finish up. I apologize if we didn't answer all of your questions, but basically, like I said, it's a great session. So couple real quick notes. First, go to delta.io. And if you want to know more about the understanding about how Delta Lake works, we actually had a VLDB 2020 paper that just was published on Delta Lake, high performance asset table storage over cloud object stores. So please be looking at it. It's a great paper. We dive deep into it. And I did want to finish up that basically for next Tuesday, we have the Data Collab Lab with Franco and myself. We're going to be doing smart SQL queries powered by Delta Engine on your Lakehouse with Dylan Bostwick and Mary Grace Mesta. So that's it for today's session. Again, thanks very much to Louis for this awesome session. Please do chime in with comments or questions directly into the YouTube Live. That's where we're going to follow up on the YouTube link.
Definitely.
So again, yeah, Louis, thanks very much. Anything you want to say before to finish it up, Louis?
No, I want to thank everybody for their time. I apologize I went right up to the window, but I felt it was important to go painfully through all those details. So I wanted everyone to understand and see what happened. But yeah, definitely, they can post the questions out on YouTube, right?
That's exactly right. They can post the questions
I'll
on
go
YouTube
out there and I'll answer them out there. So please post your questions and let me know what your thoughts are on the topic here, and maybe things that you'd want to see next time that we can present for you on Delta Lake. So thank you, everyone.
Absolutely. Thanks very much, everybody. Thanks very much, Louis. Have a good one, everybody.